All right, here we go. Emil Jagger. Okay, so last lesson for probability. We're talking about the applications of probability. Okay, so far we've already learned that when we do a probability, we have our desired outcome. How many desired outcomes of the event? Right? Over the what? Over the total number of events. Okay, so the desired outcome may be drawing the King of Hearts. I can draw one. One card is the King of Hearts. One out of how many cards in the deck? 52. So the probability of picking a King of Hearts is 1 out of 52. Okay, we already learned that. And if I got the 1 out of 52, I could then make it into a decimal. I think it's 0.0179, which is 1.79%. But today, we're going to be dealing with probability as a decimal. That's it's between 0 and 1. 0 means it's never going to happen. 1 means it's always going to happen. So basically what we're dealing with today are the probabilities when we have already done all the work. Today's lesson does all the work for you. It goes right to this answer here and says, hey, the probability is 0.0179. So with that number, what we can do is we can find what's called the expected value. And this is one where it has a key next to it, has a star. I want you to box that out. Basically, this is what it says. The probability of the event times the total value, the total number of events, people, of times at bat, like in our example on the right. When you multiply those together, you get the expected value, the expected outcome. So here's an example. If 0.75 people drink coffee, that's a lot of people, that's most people, 3 out of 4 people. And there's 100 people in the office, that means 75 people drink coffee. You just multiply them together. So we've done all the work before to be able to find this. Remember, sometimes on the bottom, like on Wednesday, we had to use permutations. So we had to use permutations to find that total number of outcomes, total possibilities. So with this, we're already given the probability of the event. That's nice because we already learned how to do all that work. And we're going to multiply it by the total value. Some of the problems on the homework are going to be, I'm giving you pretty simple examples, but the homework's going to have some really challenging ones. You'll have today and Wednesday to work on it. And I'll give the sub on Wednesday the notes that will help them guide you through parts of it. So they'll give you little hints if you need to, because we'll work that out on Wednesday together. All right. The other bit about this, all options must add to 1, must add to 100%. Okay. So if 0.75 drink coffee, 0.25 don't. Does that make sense? If we're talking about who drinks coffee, if 0.75 do drink it, then the 0.25 don't drink it. It always adds up. So let's see. If you had a pie chart right here, well, I don't want to freak you guys out. Yeah, I'll risk it. So we look at this. If I'm just doing like a pie chart here. Wow. Ooh. See that?
That was good.
What is this side right here? This segment is what? It's about
1/2.
1/2. So everybody okay with me putting 0.5? 0.5, right? Okay. So what would you say, just give me a guess, what would this little segment be here? What do you think? It could be a guess, not perfect.
1 through 5. 10. About 16%.
I like that. Boom. All right, and then what if I were able to cut these in half exactly? What would these two, if they're the same, what would they have to be? Let's see, let's add these up. These add up to 0.66. So let's subtract out 1 because that's the total possible. Yeah. Okay. So if both of these add up to be 0.34, what's each of those? Good. They all have to add up to 1. All the percentages add up to 1 because you have to make the full pie here. Okay. Does that make sense why it has to all add up? Because what if, if you had a pie chart and somehow there was 1% left out? That's not a pie chart. That's like a Pac-Man eating little things. Did you get that? It was barely a joke. Waka waka. I thought there was a waka waka joke. All right, you guys see how the pi has that up to 1? Makes sense, right? All right. Now let's look at this a little further. There's two types of events. There's an OR event and there's an AND event. Usually the word problem will have it all kind of mapped out for you. When we have an OR, these are over there as well, but these will be up for the quiz. You add together when it's an OR. So this could be, let's see, the probability of getting into an Ivy League or getting into a UC. You would add those probabilities together, and that would be the probability of getting into this or that. Now the intersection, which is an AND situation, is going to be multiplying the two probabilities. So in our home run derby here, the first question is the probability that all get a home run on the first pitch. So what that's saying is Jane gets a home run, and Jose gets a home run, and Andre gets a home run. Okay. If it was a situation where it was, what's the probability that Jane or Jose get a home run on the first pitch, then you would be using an OR situation. So the problem's going to kind of map it out for you. Yeah, Blake?
Is it because Jane or Jose to get it is a lot higher, that's why it's using addition, whereas the chance for all of them to get a home run first time, very, very few.
I like this. Well said. Well said. So if you have a 1 in 4 chance of getting a home run, the other person has a 1 in 4 chance. Together you have a, if we're adding those together, what do we have? 2 out of 4, right? 2/4, because there's a 1/4 chance and 1/4 chance. So together, for them to have Jane or Jose gets it, that's going to be 2 out of 4, so you have 50% chance. It's better. It's a better chance. Now, we're going to look at this example here. When you're given the percentage for our home run derby, and these are pretty high home run percentages, because what do they do with the home run derby? Are they throwing fastballs? Are they throwing knuckleballs?
No.
They're throwing what?
Softball.
They're throwing out like maybe 78, 80 mile an hour. Maybe less. Not even, huh?
Yeah.
They're kind of just doing like underhand pitches. It's like a T-ball. Just kidding. So if we have .33, and this batter at the time that they're taking these stats is having 11 pitches, how many home runs are they going to get? Who can tell me what our process is going to be? What do you think? Think about this. I want to know the expected value. Think about the coffee drinking example. And how am I going to find the expected value? How many home run total is that person going to get? How many home runs altogether? Let's do it. .333 times 11. They're going to get 3.66 home runs. So because it's all probability, I'd say they're going to get about 4. So that's what, remember, this is what like a batting average is. A batting average is just what percent they get on base, right? So you can tell how often they're going to get on base based on that and how many times they're up to bat. Okay, how about this one? It is 0.3%, and 0.3 probability, and we have 10 pitches. How many home runs are they going to get?
3.
0.25 percentage, probability, and there's 12 pitches. How many hits are they going to get?
3.
Okay. So who do you think is going to win the home run contest?
Jane.
Okay. How many pitches do you think they're going to get all together? If it's fair. If it's fair, though. So maybe these guys aren't done yet, right? If this guy got 12, they all get 12, right? So whenever they took these stats, it was that number of pitches so far. So let's see. Maybe this person is definitely going to get another home run if they're this close to be at 12, right? So I think this person is going to win. This person, this person is going to end up 2 more at bats. Next Actually, it gets a 12 divided by 3 is 4 as well. So I think these two might actually tie. But Jane's a little bit ahead. Andre definitely lost because he only has 3 and he's done. Okay. You see how we can kind of reason through a lot of these components. We can reason through a lot of this. A lot of what we're going to do in the homework is a lot of just reasoning through. You have to read it a few times and let you work in partners. Let's find this one probability and then we'll take a look at the workbook. Okay, listen up. Probability, all get a homer on the first pitch. Okay, so it's their first at bat, right? Here's their percentage home run. So if they all get it, is that an and? Is that either and or an or situation? If they all get it. And, right? So it's probability that Jane gets a home run, and Jose gets one, and Andre gets one. Okay?
Oh my God.
So what is the probability that Jane gets it? If I express that as a, I can do it as a percent.
1/3.
1/3. I'll do it as fraction. 1/3 times, since it's and we're multiplying. What is 0.3 as a
10. Right?
Yeah, you do it that way. Yeah, that's perfect. How about this one? 1/4. Okay. We multiply it all together. 3 out of 3 times 4 is 12 times 10, 120. So we get 1 out of 40. So you have a 1 in 40 chance of all of them getting the home run on the first try. And then from this, let's clear that out. 1 divided by 40. I want you to put your answers as decimal. 0.25. So this is the answer that I want. Because all the problems are given in decimal. They don't give them as percentage. You're going to have to just get used to the decimal version. Remind the viewers, what number gets the big old package of Oreos? 123. I'm at like 98. Who can you sign up and maybe get their Oreos?
Your mom or your auntie or your grandma.
Your mom, your auntie, your grandmother.
Your sister.
Your sister. He's like in 2nd grade.
Your significant other. Cousin.
Significant other's cousin.
Your cousin's significant other.
Your cousin's significant other.
Your best friend's sister's boyfriend.
Best friend's sister's boyfriend. Any animals allowed?
Yeah.
Who could you sign? Your goldfish's uncle. Your dog. Hamsters, like Matt. Cousins, sisters, aunts. Your mom. All right, good job. That was good, Jordan. All right, don't forget to subscribe. Oh, yeah.